Welcome back to Multigrid Methods. So we're in this chapter on convex analysis, and it's kind of complicated, new material for some of you. Um, so I want to back up just a little bit and talk about a little bit more about second derivatives and maybe do some examples or give you an example before we get on to other stuff. So remember we said you've got this map, which is usually nonlinear or nonlinear function from one Banach space to another, and we can ask the question, well, when is it going to be differentiable? We had this definition of differentiability called Frechet differentiability. If we know that that mapping, the Frechet mapping or the Frechet derivative mapping exists at certain points, then we can ask, is that mapping differentiable? And so when we asked that question, we said, well, yes, in some cases it could be, and here's the definition, blah, blah, blah. And then we went on to say, well, you know, when you have a Frechet derivative of a functional, that Frechet derivative is a linear operator, right? It's no longer at every point, it's kind of a bounded linear operator as a structure. But when we take a second derivative, we get a bounded bilinear operator, which is kind of a weird thing. And it turns out that this bounded bilinear operator is also symmetric. So that's the first piece that we want to remind ourselves about. Now, we also discussed this concept of coercivity. So I'm backing up maybe slightly more than I need to, but it's good for us to remind ourselves of what it means to be a coercive function. I drew a picture which really encapsulates what's going on for these recursive functions. Basically, the picture looks like this. If I have some Banach space, well, let's see, this one is, yeah, I guess it's a Hilbert space, V, and E is real valued. And so I'm going to just pretend this Hilbert space is actually the real line. And so a coercive function is one which goes off to infinity as V, the norm of Vn goes to infinity. So basically what a coercive function looks like is one which has at infinity, it's got to be going up. And well, plus infinity, it's going up, and minus infinity, as you're going off to minus infinity, is also going up. But in between, at around zero, it could be having any sort of properties. It doesn't even have to be really continuous. But this is what a coercive function looks like. It's going up as we're going off to infinity. It's actually not just going up, it's blowing up, right? Well, I'm going to show you that the second derivative can be used to characterize this kind of blow up. But before I do that, I'm going to give you another version of Taylor's theorem. But this time we're going to do Taylor's theorem just for real valued functionals. So suppose that V is a Hilbert space and EV, we can think about EV as being an energy functional, which is taking objects from the Hilbert space and mapping them into R. So it's assigning a number, just like an integral would do. We're going to suppose that this is twice continuously Frechet differentiable on a convex set K. Then for every VW in K, we have this version of Taylor's theorem, which looks like Taylor with an integral remainder. But now the integral remainder is not at the first order like we had previously, but at the second order. So we have EW is equal minus EV is equal to DEV acting on W minus V. So this is the first Frechet derivative evaluated at V. V is kind of our expansion point. And if you like, you can take this guy and move it over to the right-hand side, and it changes its sign from minus to plus. So this is the first derivative piece, but the second derivative piece is a little bit funny looking, I guess. It looks like this. This is our second Frechet derivative, and remember, it has to be evaluated at a point. So the point is at V plus TW minus V. So this point here is the interpolation between V and W, right? Because if T is equal to 0, then we just get V, and if T is equal to 1, then we get W because we have V plus W minus V, the V's cancel out. And now I'm integrating over T from T equals 0 to T equals 1. So this looks a lot like our integral remainder theorem where we were, well, in a previous proposition where this was only involving the first order derivative. Now it involves the second order derivative. Notice that we're acting on two pieces here, right? Because the second Frechet derivative of a functional is a bounded bilinear operator. It's got to have two things it's operating on. This is the value of the operator at that point. And now what is this prefactor here? This prefactor just has to be there to make the Taylor with integral remainder come out correctly. So moreover, for every h in V, we can also write this. Okay, in fact, this is just a very slight modification of this. In fact, you can prove it just by swapping some things around and then adding things together. So this follows from this, okay? And we're not going to discuss why or how because I'm just going to state this theorem as if you've seen it before or as if you could go look up the proof in another book. So this is one of those ones where we're going to look to the references for the proof. All right, so second order version of Taylor's theorem, or Taylor's theorem with integral remainder. So let's apply this, and we're going to apply it in a couple of other places, or it can be applied in a couple of other places as well. We're going to apply this to prove that if we know some information about the second derivative of a functional, then we can show that E is coercive. So suppose that my functional is twice continuously differentiable on V. If there is a constant mu greater than 0 such that for every V and W in V, we have the following estimate, then E is going to be a coercive functional, okay? E has to be a coercive functional. So remember, that means that it's going off to infinity as the norm of V is going off to plus and minus infinity. So how can we prove this? So owing to the previous proposition, shouldn't have this reference in here. Usually we drop the references in the slides. So because of the previous proposition, we have or can use that Taylor's theorem with the integral remainder at second order. We're going to use the following 2 points. So we're going to, remember, there are 2 points allowed here, W and V. We're just going to set V to be equal to the 0 point from the space. Okay, allow V to be the 0 point in the space. It's a Hilbert space, so it has a 0. Okay, there's some object in there which is the 0 in the Hilbert space. In fact, that's true of any linear space, right? Now, let's see. So if we do that in the last proposition, then we get just this. And the simplification comes from there's no W minus V anymore because V is 0. We're evaluating at 0. Now, this derivative, this first Frechet derivative may or may not be equal to 0. And in general, it's not. It's just some bounded linear functional. And we have to operate on arbitrary elements W, and this is the term that comes out in the Taylor theorem with integral remainder. This guy simplifies as well. Remember, this is W minus V and W minus V, but V is equal to 0. This also simplifies because V is equal to 0, right? So now what are we going to do? Let's take this term here And it looks like we're actually applying Cauchy-Schwarz to this, but we're not actually applying Cauchy-Schwarz. We're just using the fact that this is a bounded linear operator, and we're going to go what? We're going to go this way. We're going to say that minus d e evaluated at 0 against w. So this is the duality pairing. And remember, duality pairing doesn't mean it's actually an inner product. It just means that this linear functional is acting on that particular um, vector from the Hilbert space or point in the Hilbert space. So we really want to rewrite this as minus dE0 W. Okay, it's just acting on. It's remember this is a linear functional, and linear functionals take points to the real line. So now I could put an absolute value around this if I wanted to. It doesn't matter. So now I'm just going to use the fact that this is a bounded linear operator. It's a bounded linear functional. So I can use the norm. So that's going to be dE at 0. And the norm is going to be measured in V prime in the dual space norm. So that's also called the operator norm. I need to slide that out just a little bit. Okay, that's the operator norm times the norm of W in V. Okay, so this is just a property of operator norms. We've also called this in the classical, in the linear algebra setting or the numerical analysis setting, this was our what we call continuity of the norm, okay? Continuity of the operator norm, essentially. Well, now what we do is we're going to multiply by a minus sign, and that reverses the inequality. So multiply by a minus sign, and that reverses the inequality. And so now I can take this term, which was here, and I can replace it by this term, which was smaller. So that's what I get. But now I'm assuming this, right? For some constant, there's a typo, right? And the typo is this should not be a C, this should be a mu. Where'd that C come from? Well, it shouldn't be there. That should be a mu. So now I'm going to put that mu in. So let's do that. We're going to replace all of this with all of that, right? For any V. Now notice that this is mu is independent of V and it's independent of W. The only W dependence comes there. So I'm going to take this part of the integrand and I'm going to replace that with something which is smaller. Now, I'm only allowed to do that as long as this function here is also non-negative, and it is. So notice that 1 minus t for t between 0 and 1, that's always going to be a positive number. It's a fraction, right? It's a fraction between, on one hand, it's going to be 0 whenever t is equal to 0, and it goes down, or sorry, whenever t is equal to 0, it's 1, and it goes down to 0. But it's always positive. So I have an integrand here, right? And I can replace it with something which is going to be smaller. So that's the idea, but still positive. So we're going to take this object here and replace it by mu times the norm of W squared, right? So now all I have to do is integrate that. So because this term is now going to be independent of t, completely independent of t, and so I can bring that out once I do this replacement. I can then do the integration over t from t equals 0 to 1 of this function, 1 minus t, and I'm going to get 1/2 precisely. So that's where the 1/2 comes from. The mu, of course, comes from when I correct this. I correctly have a constant mu there. And now I'm just going to examine this function. Now this function is just a function of this norm W, norm of W. Now the norm of W can't be negative. It can only be positive. So it's a little bit like looking at a function, which the function is basically something like this. It's f of the absolute value of a number. Let's call it x, right? And that is equal to some constant, don't care what it is, minus some other constant, let's say C1, C2, absolute value of x. Well, this guy here could be problematical because, well, this could be negative. This thing could get really negative, right? Because C2 could be negative. We don't know what is the sign of that. Well, actually, we do know the sign. C2 here, that's going to be positive constant, so negative. This gets really negative. But the nice thing is we've got another term which is going to rescue us. Mu over 2, remember mu is going to be assumed to be positive. And so mu over 2 times the absolute value of x squared. Now, at infinity, absolute value of x quantity squared is going to beat absolute value of x plus or minus. It doesn't matter what the sign is on this guy. This guy wins in the end. And so this guy goes to infinity. So this quantity has to go to infinity, which means ultimately that that quantity has to go to infinity as the norm of W. Of course, I'm using norm of W here and uh, not norm of or absolute value of X. I was just giving you a comparison. Here, this term is going to win at infinity. It's going to beat any other terms which could possibly be negative. But this is always positive. We always have to be observing that EW is going off to infinity. So that says that the functional has to be coercive, right? So this gives us a nice, easy test to see if we've got a coercive functional. Now, last time I got deep in the weeds of calculating with this example, and I didn't give you the answer. I said you could figure out the answer. So I decided to just, we did the calculation previously, and so now I've decided to just give you the answer here, and maybe I'll make this a homework exercise at some point. But the idea is we're looking at the following problem. Suppose that n is an integer or a positive integer, and A is an n by n symmetric matrix. So this subscript sim means symmetric matrix. Then we're going to define for every x the following functional. E of x is equal to 1/2 x transpose A x plus a quarter times the sum I equals 1 to n xi to the fourth power. Okay, so each one of these terms is going to be positive, taking xi to the fourth power. And remember, this is for a vector, so it has n components. So I take each one of the components, I raise it to the fourth power, I sum them all up, and then I multiply by a quarter. So that gives me my my second term. So this term is what we call quadratic, and this term is what we call non-quadratic, okay? Now this functional turns out to be twice continuously Frechet differentiable, and the proof of this is not that hard, actually. You can apply the definition, and you can apply it twice. And you can even apply the definition of continuity to show that each one of the derivatives, first two derivatives, are continuous. Now, you probably remember a couple of things from your days taking Calc 3 or vector calculus, whatever you took at your home university. And you remember that there's this thing called the gradient, and there's this other thing which is called the Hessian. So for this particular functional, the gradient works out to be, and you can do the calculation. Basically, the calculation I showed you last time is a good way to do this. The gradient of E at a point Z is exactly equal to A times Z. So that's matrix A times the vector Z. That gives you a vector. So this is a vector, okay, the gradient vector. And it's AZ plus the vector, which is just all of the components of Z raised to the third power individually. So the first component is the first component of Z raised to the third power. Second component of this vector is the second component of Z raised to the third power, and so on, all the way down to the last. So this is a vector plus a vector. So this gives you the gradient vector, okay? Now for the Hessian, how do I compute the Hessian? The Hessian, you probably remember, was the matrix of all the second derivatives. And it's not too hard to show that the matrix of all the second derivatives for this guy is this following symmetric matrix. So it's equal to A. A was assumed symmetric from the beginning, plus this symmetric matrix, 3 times the diagonal matrix, which is comprised of the following diagonal entries: z1 squared, z2 squared, all the way up to zn squared. Okay, so it's diagonal, but it has these weird diagonal entries. So this matrix, you can observe right away, has a piece which is actually positive, that or at least non-negative. So as long as z is not the zero vector, then this is always going to be non-negative, have non-negative entries on the diagonal. But we can also see that that gives us a positive semi-definite matrix, symmetric, positive, and semi-definite. Every diagonal matrix is clearly symmetric. The fact that it's positive semi-definite is just it just follows from the fact that all the diagonal entries are greater than or equal to 0. And of course, the 3 out front means we scale all the elements by multiplying by 3. And of course, if I take 2 symmetric matrices and add them to each other, I get a symmetric matrix. And then one can prove that actually the first Frechet derivative, remember what is Frechet derivative? For every z, it's going to be a linear functional, bounded linear functional. And in fact, in this case, it's just the gradient operator, or it's the action of the gradient operator multiplying or going together with the dot product with any vector. So the action of this inner product on any x is just equal to x transpose times that gradient. Well, it's just uh, remember, we view every bolded vector as a column vector, so x transpose times this or times this vector. So this is really just the dot product. I could rewrite this as equal to grad E z x in the 2 inner product, right? So it's just a Euclidean 2 norm. Now, what about the second derivative? You can show that the second derivative, remember, the first derivative, first Frechet derivative is for every z is a bounded linear functional. Now, the second derivative for every z is a bounded bilinear functional, meaning that it operates on two vectors or 2 points from the space. In this case, it's 2 vectors. So when I multiply by an x, that gives me actually, or when I act on x with this guy, that gives me itself a bounded linear operator, or bounded linear functional in this case, and I have to pair that through the duality pairing with a vector in order to get a real number out. And effectively, in the end, that says that this operator is just a bounded bilinear functional. When I act on these 2 points, x and y, then the action just becomes y transpose times the Hessian matrix times x. This really is matrix times vector. Of course, matrix times vector gives me a vector, and then when I take the transpose of one vector against another, that's just the dot product. So this one I could rewrite as HE at the point z times x. So that's matrix times vector. That gives me a vector. And then finally y. Okay, in the 2 inner product. All right. And now the Hessian matrix is symmetric, so that allows me to interchange the positions of x and y as I need to. Right? It's symmetric. Now, if A has a little bit more structure, if A is also positive definite, then this is positive semi-definite and this is positive definite. That says that the Hessian matrix has to be positive definite. Okay, strictly positive definite in this case, because that's strictly positive definite. And if I add on to a strictly positive definite matrix a symmetric positive semi-definite matrix, then I get strictly positive definite result. So that says what I just said, that HE, the Hessian matrix, is positive definite at every point Z. Point doesn't matter where we're taking the derivative. I'm always going to get a strictly positive definite matrix. Okay, so what does that say? What do we know about a strictly positive definite matrix? Well, one thing we can say about a strictly positive definite matrix is that if I take HE, um, let's see. So it's known that HEZ is, if it's strictly positive definite, then what do we know? Let's take X transpose X. Then, of course, as long as X is not equal to 0, then we have that, right? But actually, we can go a little bit further. It's easy to show, or maybe you recall that it is possible to show at least, that this is, there exists some mu such that this is true for a positive definite matrix. Okay, so this is, we're dealing with a Euclidean case here, so it's the 2 norm of x squared. Okay, as long as x is greater, or sorry, as long as x is not the 0 vector, then this is always going to be positive, right? So you can actually use this intermediate step to show that this is always positive. Now, how do I prove something like this? Actually, what I can do is I can show that this is true with the smallest eigenvalue. So mu is actually can be replaced with the smallest eigenvalue, and that's how you can do this proof. Now, but we had a result not too long ago which said that if I have something like this, right? In fact, we had it written in a slightly different way, and it's right here. So the second derivative of E, same E here, acting on the same point twice, WW, is greater than mu W, whatever the norm is on the space squared. So, in fact, we now know that this has to hold for our current example. This says that this function is not only, well, it says that it's not only twice differentiable, but it's also going to be coercive. Now, the one thing I haven't shown, right, coercive is listed there, but the one thing I haven't shown is that actually E is also strictly convex. And I'll show you that momentarily, that's also true. Okay, well, so now we are officially into the second section, even though uh, truthfully we started here into this section last time. So I'll just thumb through a few of these things. So we proved this last time, that if I combine convex sets in certain ways by taking certain unions or certain intersections, or if I combine them in linear combinations, that the convexity of the set its convexity of the sets is retained. Okay, so we went through the proof of that, and so we also talked about this proof, this result here called Mazur's lemma, and I want to emphasize this once again because it turns out to be rather important. So we stepped through this fairly carefully. So let V be a Hilbert space and K a subset of V. If K is convex and it's also closed, then it turns out to be weakly closed. So that's what's called Mazur's lemma. Mazur's lemma. We'll refer to this more than once in the coming slides. So let's just say it one more time. V is a Hilbert space. K is a, so the picture is like this. There's our big space V, And our convex set is like right in the middle of that thing. Make it look like a convex set. K. Um, if K is known to be convex and also closed, then we know that it turns out to be weakly closed as well. Okay. If K is convex and it's closed, then it's weakly closed. The converse we discussed just above this. If we know that a set is weakly closed, then it has to be closed. So we talked about that at some length last time. Okay, now the converse of this statement that we discussed is not necessarily true. We have to add a little bit of information onto a set to know that if it's closed, then it becomes weakly closed. And that little bit of extra stuff is the fact that it's going to be convex. The proof of this is kind of hard, so we're not going to go into the proof of Mazur's lemma, but we are going to use it from time to time. We talked about strictly convex functionals last time, and then we did a couple of examples. Basically, the idea here is that for a function to be convex or strictly convex, then what we do is we take, and this one is only for functionals, okay, for functionals from a Hilbert space into the real line. What you do is you make an arbitrary secant line. Make an arbitrary secant line. Let's make the secant line purple. And what you want to show is that any point along the secant line, it lies above the point on the function itself. And so what this means is I'm going to examine I've got these fixed points here and here, and so I guess that's going to be what, V and W. And that somewhere in the middle is going to be a point called x, let's say. Well, I can look at the value of the functional at x, and I can also look at the value of the secant line at x. And for a convex functional, we need the value on the secant line to always be above the value on the graph. Okay, so such functions that have this property, okay, are called convex. If this holds with a strict inequality, then we say it's strictly convex. And the function that I've drawn here is basically strictly convex. So what's a good example of that? Let's say, here's an example. So if I take E to be, let's take X to be in Rn. And E to the X, let's say, is equal to 1/2 X transpose AX. If A is an n by n SPD matrix, then this function is a convex function. Okay, this function is a convex function. It's not hard to show that. What's a simpler example? A simpler example might be, let's just do, let's do something really simple and say for x in the real line, then 1/2 x squared. Or in fact, as long as it's any positive number multiplying x squared, then this function, of course, is a parabola, right? A nice little parabola, and that function is convex. In fact, I can make it quite general, right? I could say if it's x minus k squared plus any constant, then that function is, of course, kind of a generalized parabola, and that guy is also going to be strictly convex. And we have a couple more examples. So this one, I guess I spilled the beans on. If A is SPSD, so symmetric positive semi-definite, then this function is convex, but it's not necessarily strictly convex. And the way you get a strictly convex version of that is you force A to be a little bit stronger and say if A is SPD, strictly positive definite, then this function is strictly convex. And I also gave the example of something called the support function. That function also turns out to be convex. Now, new stuff. Finally, on to some new stuff. So this is a big theorem, a big proposition that we're also not going to prove the details for. We're just going to refer to the literature on this one. This is well-known stuff. So you can go to the books that we cited in the notes and find a proof for this rather long proposition. Sometimes in other books it'll be broken up into several different results. So let V be a Hilbert space. The functional E mapping the Hilbert space into the real line is convex if and only if its epigraph is also a convex set. So now the epigraph is, well, let's remind ourselves what that is and see if it kind of makes sense. So here's a function, and the epigraph is the graph of everything which lies above the function. Okay, so the question is this function that I've drawn here as an example, is this function convex? And the answer is no, because, for example, I could take any 2 points from the space and draw a line between them, and I could find a point on that line which is not in that set of the epigraph. Remember, the epigraph is the cross product of the points from the domain and the points above the graph. And well, in this case, it's not convex. Now, if the epigraph is a convex set of this product, for this product set in this product space, then the function has to be convex. And conversely, if the function is convex, then the epigraph must also be a convex set. If the functional is convex, then for every alpha in R, the sublevel set is also a convex function. So here's a maybe a picture of what this looks like. So I hope you all know what a paraboloid is. Let me draw this on the next page. Let's add a page here. All right, so I want to add what's called or look at what's called a paraboloid in 2 dimensions. And so let's see, this is X and Y. And so the paraboloid is something like that, right? It's a paraboloid sheet. Now I can look at something called the level sets of this guy. So basically I'm going to pick a number in the range, and I'm going to ask, well, what values of X and Y are in the domain, which when I plug them into the function, give values less than the chosen value. So I'm going to come up here to alpha, the point alpha, and so I'm looking for points in the space X and Y. So in this, let's say this function is E of X and Y, right? That's that guy there. So now I'm going to look at the set of all points in this space. And this is called the, what did I call it? Level, yeah. Level alpha of E is equal to the set of all points X and Y from R2 such that what? E of X and Y is less than or equal to alpha. That's called the sublevel set, right? So, well, we can kind of identify right away what are the points where we're exactly equal to alpha. That's going to be in R2, and it's going to be down here on the in the plane, and so we can let's mark that point, maybe that one, and this one out here, and it's going to be in general, for a paraboloid, classical paraboloid, that is going to be some sort of ellipse. And now this set is, we're looking for, that's where we're exactly equal to. So this set here is the set where we're exactly equal to alpha. That's called the level set or the level curve. Now we're looking for the sub-level set of that. So that's everything inside that ellipse. That gives me what's called the sub-level set for alpha. That's everything inside there, right? Sub-level set, you pick alpha, and you're going to determine what is the boundary. And then for this case, it's everything inside of that boundary gives me what's called the sub-level set. Okay, well, that's the complicated picture. Now, the result is if the function is convex, then for every alpha in R, the sub-level set is also going to be convex. Now, some values of alpha are going to give us the empty set because there'll be no values of x and y such that e of x and y are less than, let's see, is that true? Let's see. Let's see, if I pick alpha down here, right, then yeah, right, there's no values of x and y such that e of x is less than x and y. So that would give us the empty set. But the empty set turns out by definition to be convex, okay? So more generally, you're looking for these sub-level sets where alpha is in the range. So in this case, the range is any number bigger than the smallest one for a paraboloid. Okay, so if this function is convex, then for every alpha in R, and specifically every alpha in the range, to get a less trivial case, the sublevel set is convex. Okay, so that's another we're not going to prove, but could be proven. Okay, so here's another one. If we, let's see, suppose that we've got a bunch of convex functionals, okay? E of alpha, and alpha is some index. So for example, it could just be two functions, right? So I'm going to draw you a nice picture of this. Then if we take the supremum over those convex functions, then the resulting supremum is also going to be convex. Okay, so this one's another one that I think a proof by a picture could be good. So let's just do the simplest case. So we're going to have the real line here, and let's have two convex functions on stage, please. So the first one is going to be a simple parabola, and the other one is another simple parabola. Okay, so let's figure out what does the soup function look like for this guy. So the soup function is, of course, going to be, you have to look at for every point, you're going to take the supremum, say, of this point and this point way up here. It's way up here, right? So, of course, that's going to be that point way up there. What about if I'm at this point? Okay, what's the supremum of these 2 points? Well, it's this guy. What about if I'm right in the middle or right at the intersection point? So that supremum, well, it's just going to be that. And then keep going. Take the supremum again of this point and that point. Well, it's got to be this point. So the supremum, of course, is just this upper envelope here. Okay. Now, if I have two functions and I take the supremum over those two functions, then the resulting function is going to be convex. If I take the supremum over 3 or 4 or any number, it doesn't really matter. The result is always going to be convex. And so that's what this result is saying. If every E alpha is convex, then the resulting supremum is also going to be convex. 4, if the functional E is convex and it's lower semi-continuous, then a very nice property emerges, which says that it's also weakly lower semi-continuous. And this has to do with the result. Basically, this is related to Mazur's lemma that we stated earlier. Let the functional E be Frechet differentiable. E is convex if and only if the following inequality is true. E is convex if and only if the following quantity is true. E of V is greater than or equal to E of W plus dE, the Frechet derivative, acting at the point W times the difference V minus W. What does this piece look like? This piece here. Well, we actually we looked at that already, or we've seen that before. That piece there is part of a piece that we've already seen. Namely, it's this part here. Okay? So, in fact, if I take this guy and move it to the other side, then all I'm left with is this remainder part here. Okay, so this piece here looks like the piece that I just showed you. So let's go back to it. It's right there. Okay? In fact, if I take this part and that part over to the other side, that says that that part, okay, has to be positive, greater than or equal to 0. So let me write that over here. So that's what I'm saying. EV minus EW minus DE is going to be at W, right? It has to be W. And V minus W. Okay. So what I'm saying is that part has to be positive if this part satisfies this inequality. So E is convex if and only if this inequality holds. And that's true if and only if this piece here is greater than or equal to 0. And that piece there is the piece that we can isolate in the Taylor theorem with integral remainder of second order. Okay, so I can use something about that integral remainder to show that that is going to be greater than or equal to 0, quite possibly. Okay, so this is convex if and only if that inequality holds, and this does not have to be strict. But if it is strict, then what we know is that E has to be strictly convex. E is strictly convex if and only if the inequality is strict, but the only way the inequality can be strict is whenever V and W are not equal to each other. Because whenever E and W are equal to each other, this equals that, and that part is 0, which has to yield 0. So basically it's just saying 0 is greater than or equal to 0. And the only way you can satisfy that is with an equality. All right. Next, 6. If the functional is convex and Frechet differentiable, then its Frechet derivative is monotone. And basically that means this inequality holds. Okay. If in addition E is strictly convex, then the derivative is strictly monotone, so long as W and V are not equal to each other. So this inequality becomes strict. Okay, so this is what we call a monotone, or this is what we mean when we say a monotone operator. Okay, so this is an operator, and it's actually a functional for every V. By the way, the difference of two functionals gives another functional. So this is again duality pairing here. And remember, duality pairing doesn't mean we're using an inner product. It just means the duality pairing between a functional from the dual and a point in the Hilbert space. 7. Let the functional E be twice continuously Frechet differentiable. If the second Frechet derivative is positive semi-definite, i.e. we have for every V and W, we have this inequality holding, then E has to be convex. In addition, if the second derivative is positive definite, then the inequality, um, which means that this inequality is strict, then E has to be strictly convex. Now, the way I can prove this is I can simply, I can go back to Taylor's theorem with the integral remainder. I can use this result, plug it in, and then I can go back to the fact that this important piece of information has to hold. So I can use Taylor's theorem with integral remainder plus my knowledge of 5 to show that this 0.7 has to hold. Okay, property number 7. All right. So the next notion is a little bit like something that I talked about earlier. It's kind of an analogy. Remember I said or earlier that if I have a positive definite matrix, let's say strictly positive definite, then I can show that X transpose AX is greater than or equal to mu times, so this is just in matrices, okay, times the 2 norm of X squared. There exists some mu positive. And that mu can turn out to be the smallest eigenvalue. All right. So this allows us to not just prove that we have positive definiteness, right? But it allows us to quantitatively say how strong our positive definiteness is. So here's an analogy for convex functions. So usually when we state that something is convex, we don't necessarily say, we don't always say how convex it is. So remember we said previously that if the function or the derivative is monotone, that means that this duality pairing is greater than or equal to 0, then the function was convex, right? But now we can say kind of quantitatively how convex it is, all right? So we say that E is strongly convex with constant mu positive if and only if for every V and W in the Hilbert space, then this duality pairing is greater than this norm squared, mu times the norm of the difference, W minus V squared. So this gives a quantitative measure about how strongly convex something is. In fact, this is kind of like this constant is going to be important to us. And so we say that it's kind of on the weaker side of strongly convex if this is close to 0. That's a little bit like saying the eigenvalue, the smallest eigenvalue is really close to 0, right? And so we know, remember if we had a stiffness matrix or we had the example was the stiffness matrix. In the classical setting, we had one of the eigenvalues being 4, the maximal eigenvalue, and the smallest eigenvalue was positive, but just barely so. As the step size parameter h got smaller and smaller, that eigenvalue got closer and closer to 0. So that was some sort of measure of how ill-conditioned the matrix was, right? So what you want in practice is you want that value to be, really pretty far away from 0, not super close to 0. And that's going to really tell us what is the strength of our strong convexity. And the same is going to apply here. Okay. So we want this guy not to deteriorate to 0 as certain parameters change. Now, I will say this is what we call strong convexity. Other books use the term elliptic for this for this function. Okay, so it's elliptic if and only if this is true. Now, the function null that is in this position is actually the difference of two functionals, is the difference of the two first Frechet derivatives at two different points, x and v. Okay, so just keep that in mind. Strongly convex. Okay, so now we have a theorem. Let V be a Hilbert space, and let's suppose that E is a strongly convex functional with the constant mu. So mu has to be positive. So, don't forget that. Then, for every V and W in the Hilbert space, the difference between the function EW and EV is greater than this sum of things. Okay, so this is the same term that appeared previously here as a lower bound for our monotonicity measure. Okay, and so we want to prove this. Okay, this is the same. Actually, it's not exactly the same, right? This is mu over 2, and this is mu without the division by 2. So how can we show this? All right, so is it if and only if? I think it's just, no, it's just one direction. So if it's strongly convex, then that implies that. All right, so let's prove this using Taylor's theorem with integral remainder. So Taylor's theorem with integral remainder says that basically that top line, that's Taylor's theorem with integral remainder. Now what I'm going to do, I'm going to notice that this integrand here can't be moved outside of the integral because if you drill down to it, kind of everything depends on t. There's no constant term which is independent of t. So what I want to do is I'm going to add and subtract this term right here. Add and subtract that term. What do we get if we add and subtract that term? Um, well, let's see. Do I have a mistake here? I think there's a typo here because the T should not be out front, right? This T probably needs to come inside. I think. I think the T needs to be inside of here. So it doesn't seem to make sense if it's outside, right? So, all right. So I know that I need this term to come out. So let's try fixing this up. See if I can fix it up without too much damage. I also know that this should be correct. So yeah, I'm okay with that. But how in the world do I get t outside of there? That's the integration variable. That doesn't look good. That doesn't look good. So, all right, let's see if I can rescue this incorrect calculation. So, if I add this term and then I subtract it, but when I subtract it, I bring it into the interior, what do I get? What do I get there? So this remains unchanged, correct? That remains unchanged. I'm going to take this term and I'm going to inject it into the interior. If I multiply by, let's say, if I take this term here, so I think the only way I can do this, the only way I can rescue this calculation is if I make a separate sheet of paper. I'm not going to be able to do it otherwise. Okay. So, we're going to start out with that first line. So E of, I don't want to use blue. Let's see here. Let's use black. And let's see, was it? Yeah, it's W minus E of V. And this has to be equal to integral 0 to 1, duality pairing dE. What goes on the inside? It's going to be V plus T W minus V. And we need to act on that in the dual pairing W minus V. That is all dependent on time, right? So the thing we want to add and subtract is going to be DEV. So that object is the Frechet derivative. It has to be paired with a point from the space. And the point from the space what we're going to use is W minus V. Okay. Well, if I add it, I have to subtract it as well. So let's get really dumb here. W minus V plus, let's use the power of, some of you suggested we use notability when we do our prelims. I think that's a neat idea. Copy, paste. Unless you're not very, let's see, undo. Unless you're not very good at notability, which I just proved maybe I'm not. Copy and paste. There we go. All right, now I'm gonna keep that part, but I'm gonna rewrite my integral. Now, when I do that, let's see, I can combine that directly in here because this is going to be a linear functional acting on the same object. So I should be able to write 0, 1. Not a vector that way. Now, what do I want to subtract? D, E, V. So the question is that the one that I want in there? And it looks like not exactly. Looks like I want to put T in both of them. How would I do that though? Well, I have to divide by the T, don't I? I have to divide by a T. Right. So now, okay, that's fine. Copy and paste. So if I really do want to put that T in there, I'm just going to treat T as if it's some, well, it's just some constant with respect to what I'm about to do, right? I'm going to put a T in here. Why can I do this? That's because this whole thing is the difference of two bounded linear functionals, right? Something from the dual space. But I really have to divide the T at this point, right? That's the only way that's going to work. Now, what am I going to do? What am I going to do next? So let's see if I can rescue this at this point. So now I'm claiming that I think what I want to do, right, is look at this difference here, right, and see, do I have a difference of, say, monotone operators or something like that? I need to use I need to use that. Right. So this part here has to be the same. No problem there. And this part here has to be the difference of the evaluations at these two different points, right? If I want to replace that by that, what do I need in the interior? So let's look at that. Okay, the thing I'm operating on with that is there. And the difference of this point minus that point is going to be precisely t times w minus v. Yeah, so it works, right? It works out. I need the difference of these two things to be exactly that thing there. And if I do that, then I can replace that. Okay, so the only error here is that this 1 over t needs to be on the inside. 1 over t needs to be on the inside, correct? Now, once it's on the inside, then that 1 over t just cancels. Okay? Yeah, so that that explains the error. So this 1 over t doesn't make sense on the outside. That's the integration variable. It has to be on the inside. But now t is a positive number, right? T is positive. It's between 0 and 1. And the only way it's equal to 0 is in the case where t itself is equal to 0. But in that case, that's just 1 point. And so I don't have to worry about that. Otherwise, t is positive, and I can cancel it with that positive number inside that norm. So I've exactly used my strict or my strong convexity statement. And now once the t is gone, then this is independent of t completely, right? It's completely independent of t. So why do I get a t to the 1/2 power there? Or sorry, where's this 1/2 coming from? Let's see. Well, I'm integrating from 0 to 1, the constant function 1. So that gives me just t. What
But
am
how
I
are you
missing?
integrating the function t because you have a t squared?
Oh, yes, 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 yes. Thank you. You rescued me. You rescued me. I was canceling the t squared with a t, but it's actually t, right? So I integrate t in the end, and that, of course, becomes t squared over 2, and that's where I get the half. Thank you. Thank you. You rescued me. Right. Okay, so that proves 7. That proves 7. And so what else is there here? So next, we see that whenever W and V are not equal to each other, then 7 is going to imply that, right? Because the only way that W and V could be equal to each other, um, let's see, so the only way I can get equality here is when W and V are equal to each other according to 7. So let's go back. Why is that true? Well, if W and V are equal to each other, then that guy is equal, right? This guy will be 0, and so this guy um, is going to have to be equal to 0 as well. But now let's suppose that V and W are not equal. So that's clearly true. Whenever W and V are equal to 0, we definitely get this. Um, but why do we have strict convexity? Um, oh, right. So the reason is because if W and V are not equal to each other, then this guy is strictly positive, right? Strictly positive. So that guy we can replace with is strictly greater than 0. So that means we can continue this and say that that's strictly greater than 0 as long as W and V are not equal to each other. So yes, of course, 7 implies that. But by our previous proposition, if we have strict inequality there, then that shows that E is strictly convex. Okay, so easy peasy, I guess. And calculations, okay. Um, Now, this I'm going to leave for next time because I'm out of time. And so I want to say a little bit more about this and be a little bit more careful in this situation here. So let's, so we're not quite through with this proof, and I'd hope to get through the rest of this set of notes. Not quite there, but I'm going to stop there. You guys can turn your cameras back on, and I want to take a little bit of time to explain this, and so we'll pause there, and I'll take any questions you guys have.